Hello, everybody. Hey, we are on our week 2, lecture 2, and this is a short lecture that is going to talk about changing the 4 kinematic equations that we have already talked about last week, and we're going to just change them into the vertical. Pretty easy, but a lot of what we do in the kinematics is going to deal with up and down, and if it deals with up and down, then we're going to deal with gravity. Okay, and that's really where we're going. And this should be fairly short, and I will do an example. I'll do an example of that and give you kind of some of the pitfalls and things to look for. Okay, so in our equations that I've given you, we said average velocity is equal to change in position over time is equal to v final plus v initial over 2, and we call that equation number 1. Okay, and equation number 2 is going to be v final is equal to v initial plus at, and equation 3 is going to be delta x is equal to vit plus 1/2 at squared, and equation 4 was equal to v final squared is equal to v initial squared plus 2a delta x. Okay, now you guys can see there that this is, I've done this all in terms of x, which is obviously going to be horizontal. Okay, and we also talked last week that it could be in some other equation like y or r or some other thing like that. But when we're specifically dealing, going perpendicular to the surface of the Earth or perpendicular to the surface of another large planet or moon, okay, then we're obviously going to have acceleration that we are used to. Okay, so these equations right here are just going to change, very slightly. They will have the same pattern. And then you will realize that you can just, in your own head, just adjust this. So, okay, our first equation is going to be our average velocity is equal to change in y over t, which is going to equal to v final plus v initial over 2. Now, sometimes, and we were going to see this pretty quick, probably by the end of the, maybe even by Thursday, we're going to be doing problems that are going to be two-dimensional. They're going to be two-dimensional, okay? So what we might have here is v final y and v initial y. And if we went back to these other ones, we're going to have this x, and that's going to specify which direction they're going. So, and we can see here that we will combine those two. All right. So now you guys can quickly just change this over for one, except for one thing. So we're going to have v final y is equal to v initial y plus gt. Now this g right here, okay, is equal to the acceleration due to gravity. Okay, this is the acceleration due to gravity, and it is equal to 9.8 meters per second squared. Okay, and I think your book lists it as 9.80. Okay, and I've seen other books that will give it at 9.81, and this is going to vary slightly. Depending where you are, both in elevation and location around the Earth. But for the most part, it's going to be 9.8 meters per second squared. Now, that is going to be downward. Okay, it's always going to go down. Okay. But when we're doing problems, okay, you can say down is positive. You can say down is positive. You can say up is positive. So you do most certainly need to pay attention to which direction you are describing as up or down, or sorry, positive or minus. So even though here I have it as plus gt, I'm assuming here that if I leave it as plus, I'm assuming that down is positive, okay? And if I have it as up is positive, then that is going to be negative. And we could have plus right here, and you just know that it's negative based on what you said. Again, it's kind of a preference sort of thing. So now we're going to have delta y is equal to v I y t plus 1/2 g t squared. And finally, v final y squared is equal to v initial y squared plus 2a delta y. All right, so let's do, you guys, let's do an example here. And I think we can do it right here. If we have a ball, okay, and we are going to, let's say, have 20 meters high, okay, and we have an initial velocity that's equal to 0, okay? So the question is, what is our final velocity? What is our final velocity if we drop it, okay? So we drop the ball, okay? Now, in a similar but a little more expansive view, some of the questions that we had last week where the problems did not give us specific values, but there were numbers nonetheless. And the two things being most prominent there were if it starts at rest, its velocity is 0. If an object comes to rest or stops, then its final velocity is 0, right? So if I'm asking you, if we've got a cliff that's 20 meters high, okay, and I want to know the velocity when it hits the ground, I'm not talking about after it hits the ground where the velocity would be 0. I'm talking about as it hits the ground, okay? So if we're going to use these, we're going to sample from these equations right here, okay? And I said last week that if you end up knowing 3 variables, then you can solve for what you want. You can solve for what you want. All right, so now my question to you is how fast is it going? Well, I've only got, I've only got 2 variables that are listed, right? And I need 3. Well, what is our 3rd variable? And it's g. So whenever you drop, kick, shoot, anything like that, drop, shoot, kick, throw, launch, any of those things, you know that acceleration is going to be g, which is going to be 9.8. This is sometimes called free fall, okay? And we are going to ignore air resistance. Okay, we're going to ignore air resistance. Now, as I can show you later, and this is going to come up, I think, in chapter 4 or 5. We're going to talk a little bit about air resistance, but it is a differential equation. It gets kind of messy here, as you will see later. All right, so it's very good in this process of doing problems, okay, is to draw a picture, okay? Now, it becomes much more imperative to draw a picture as we move forward, okay? It's not quite as apparent when we're doing one-dimensional kinematics. But we have an initial velocity of 0, a final velocity, which is what we're looking for. We do not know the time. We do know the displacement. And if we put a d right there instead of delta y, as long as we know what that is, displacement, then fine. Even if you put distance, because they're all going in the same direction, at this point, distance and displacement are going to be the same. Okay, all those things being equal, and then we finally, what else are we missing? We have acceleration, and we know that that is g, which is 9.8. Now, at this point, which direction is positive? Now, it actually makes more sense to call down positive because everything is going down, all right? If we start talking about throwing something up, if something is going up, gravity is always going down. That's where you really have to pay attention to your signs, okay? So if we use, let me see, which equation can we use? We want the equation that, this was 20. We want the final, okay? So we can't use equation number 2, and there is no acceleration in this problem, and we don't have time, so we can't use equation 1. And we don't have time, so we can't use equation number 2, so we're going to use equation number 4, okay? So we're going to have v final squared is equal to v initial squared plus 2g plus 2g delta y, okay? Now, since we are looking for the final velocity, okay, then we can just solve by taking the square root, and we are going to equal to, well, the initial velocity is 0, so that's going to go away. So that's going to be 2 times 9.8 times 20. And then we're going to take the square root of that. Now, we can kind of quickly see here, 9.8 is very close to 10. It's very close to the value of 10. So if we said 2 times 10 is 20 times 20 is 400, and the square root of 400 is going to be 20, okay? Now, the fact that we are a little bit less than this 9.8 here, our value is going to be just a smidge under 20 meters per second, okay? So we're going to have, and if we take our calculator here, so 9.8 times 2 times 20 is going to equal to 392, and we're going to take the square root of that, and we're going to get 19.8. Okay, so our velocity is 19.8 meters per second. All right, now, what if we said that up was positive? If we said up was positive, how does that change? How does that change the problem? Okay, well, if we started here and said that this was up, and we would now say that we would go down. So our displacement would be negative 20. If we said up was positive, we would say our acceleration was negative 9.8. So now we're going to get 2 negatives that are multiplied, which is going to turn to positive, okay? And we're going to get the same answer right here. But if we said that this was up, then our final velocity should be negative. It's going to be going down, right? So our value should really be negative 19.8. So do we have a problem mathematically here? Okay. Do we have a quick, easy solution to this? And the answer is yes, because the square root of 392 is going to be 19.8, but it's also going to be negative 19.8. It's because we get that plus or minus when we take the square root. So that is where that you've got to pay attention to what values you are talking about. Okay, which direction you said was plus or minus, and what we could really easily do to figure this out, okay, is instead of saying plus or minus, we could signify it that it's going downward. When we get into two-dimensional kinematics, it is going to turn into angles, and we will be doing angles with sine, cosine, and tangent. All right. So you guys, one last example here before we go. Now, let's say that this is 20 meters, and now we take a ball, and we're going to throw it up. We're going to throw it up, let's say, with an initial velocity of 10 meters per second. Okay? And I want to know, okay, how long does it take? How long does it take to get to its very highest point? How long does it take to get to its very highest point? Okay, well, what do we know? We know the initial velocity is equal to 10. Now remember, when we're doing these problems here, we need to get three variables, okay? So we know one variable, so what are the other two variables? What's that? The G, exactly right. And this, now, if we're saying that up is positive, which is a real natural thing here, okay, then we do have to specify that this is negative 9.8. Okay, and this is really where it matters for the signs in particular when things are going opposite of gravity here. So that is definitely has to be negative, okay? We're looking for time. Do we know the delta y? We don't know that yet, actually. Okay, now it could be, but we don't know that because we don't know how high it's going to be before it reaches the top. So we've got two variables. What is our third variable? Tricky, but obvious. Okay, now a lot of physics is seeing what is obvious, and it is not always obvious. Okay, the final velocity is equal to 0. Okay, and again, this will make sense. This will make sense when you think about it, but you haven't had to think about it. If I throw a ball up, okay, it's going to be going up, right? And when it gets to its highest point, what is its velocity? It's going to be 0. At that very instant, it's going to be 0, and that's going to be its maximum height. Okay? Very obvious when we think about it, right? But when I give you these questions here, okay, it looks like we don't have enough information, and that's one of those keys. All right, so now we are looking for time here, and I could have asked you for time here, but I kind of want to do this. From this point of view here. If we use the second equation, we can say V final is equal to V initial plus GT. Now, I can call it plus GT and just use negative 9.8, okay? Or I can just start here and I know it's negative and just put the negative in there. That part doesn't matter. That's kind of up to you. So now we can say V final, okay, is going to, sorry, we are looking for the time, right? So we're going to say V final minus VI over negative G is equal to t. Okay, and again, I mentioned this last time, and that would be if you do all your algebra with your equations, and then it will make it a little bit easier so you don't make mistakes. So now we're going to say 0 minus a positive 10 divided by a negative 9.8 divided by a negative 9.8, and that is going to give me the two negatives are going to cancel out and give me positive, okay? And what is, that's just going to be a little over 1, right? 1.0, 1.02, thank you. So that's going to be 1.02 seconds. And if we round this, and oftentimes when I am making up a problem, I don't pay particular attention, and I should, to the significant digits here. So this right here is on that 10 meters per second is only one significant digit. And if that's one significant digit, when I get down here to the time, it would be 1 second. It would be 1 second. Now, if I put a decimal point here, okay, then we could say 1.0. We could say 1.0. And if we said 1.0 or 10.0 meters per second was our initial velocity, then we would again have to round it at 1.0 because now our gravity is got two significant digits. And again, if we said 9.80 meters per second squared, then we could include that last two there. Okay, you guys, does that seem pretty reasonable? Okay. Now, as you guys move forward here, a lot of these, when you read it, you just go, I can do this, and you can, but sometimes you're going to get stuck with these things and trying to figure it out. So your work on your thing might not look this concise. You might be having a lot of starts, fits and starts. So that's fine. Just when you get to the end, you want to box your answer with the correct significant digits and the correct units. And you guys are going to get better at that. Okay, you guys, that is it for our second lecture of the morning. All right, and we will see you guys next time. Thank you.